The root locus method is a way of understanding how the closed loop poles change for a feedback system as a parameter is being varied. And this gives us more nuanced information about what the stability looks like as a parameter is changed. Oftentimes, the parameter that we'll be interested in is actually the feedback control gain, but that doesn't always have to be the case. So the method is general, and it essentially shows you where the poles move as the parameter is being varied. And this could be a feedback control gain, or it could be another parameter of the system. We're going to talk in the next video about sketching rules, and it may feel like these are a little bit archaic, but by understanding some of these basic sketching rules, you'll be able to understand how adding a zero, adding a pole, or changing the location of these poles and zeros can make a big impact on essentially how the closed loop poles move. And that's going to become even more important when we go to the concept of design, and it's even in the name here, when we start talking about other system performance measures other than just stability. So we said the root locus design method shows changes, how changes in a parameter affect the closed loop poles. And so we're going to talk about specifically the case where the parameter that we're going to vary is the controller gain. And so essentially this means that we're going to evaluate what happens when k is changed from 0 up to infinity and where the poles move. So we're going to look at our conventional closed loop feedback system. So here I've explicitly pulled out k, which is just, again, the number k, which is the parameter that's going to change. And then if we have any more sophisticated controller, for example, a PD or PI controller, the rest of those terms that are not going to vary with k are lumped inside that d term. So if we're dealing with proportional control, then d would just be 1. Just for generality, we're also assuming that we could have a h of s that's not necessarily 1, so we could have something other than unit feedback. And then we have our open loop plant g. And so if we form the closed loop transfer function, it looks just like this. And the denominator is the important part because that's what determines the location of the poles and the stability of the closed loop system. And so it's just this denominator that's particularly important, and we're going to call this the characteristic equation. And so the roots of that characteristic equation give us the closed loop poles of the transfer function and of the feedback system. And when we're talking about changes in our controller gain k, and our feedback system is architected in this block diagram, then the product of the plant g, the controller d, and any sort of sensor transfer function on the feedback loop, this is called the loop transfer function. And that simply just means that it's the product of all of these things around this feedback loop. And so that's why it's denoted by L. And so throughout this class, we're going to be talking about the properties of this loop transfer function. And so we're going to oftentimes break it up into its numerator n and its denominator s. And so we're going to assume for all of these cases that these have leading coefficient of being 1. Otherwise, we pull out a factor, then include that in the k term. So to find the closed loop poles, or the roots of the denominator, there are specifically the values of s that make this statement true, that make this equation equal to 0. And so we're looking at finding those roots of that characteristic equation. Now the characteristic equation, we're going to see it in a multiple of different forms. Again, essentially it just says that 1 plus k times L of s has to be equal to 0. But we're going to write L of s in terms of its numerator and denominator, and we're going to see that there are a couple different forms of this that then become useful. So we can rearrange this expression, which is the same one as in 1. We can insert the numerator and denominator, n and d, just like this. And then if we wanted to, we could multiply both sides by d of s, and that would just give us this expression, which is another way of understanding. This is going to be useful specifically when we let k go to 0. Then on the other hand, we could divide equation 3 by k to get equation 4, and this is going to be particularly useful when k goes off to infinity, because then that'll erase this term. And then finally, we can also rearrange and solve for L of s, and L of s has to be equal to minus 1 over k. So we'll see varying forms of this throughout the sketching rules and also the definition of the root locus method. So just as a quick example, we can take a look at the root locus for a open loop transfer function g of s of 1 over s times s plus 1. And here we're dealing with proportional control because d of s is just 1, and we're dealing with unit feedback because h of s is just 1. And so then the root locus would just be the roots of the denominator of the closed loop transfer function, which is also 1 plus k times the loop. And in this case, the loop transfer function is just g times 1, so it's just g. And so we have to satisfy when this is equal to 0. And we're looking for all values of k that anywhere go from 0 to up to infinity. And so if we just rearrange this, we can multiply both sides by s times s plus 1, and we get this expression right here. And just foiling out that product, we can see that this is then our quadratic equation that we have to find the roots of. And so if we use just the binomial formula, we can come up with the roots of this. The two roots that satisfy this, depending on the value of k, is given by this. And so this is for a specific value of k. And so now really what the root locus is going to do is it's going to analyze what happens as k changes. So when k is equal to 0, then we just have 1 under the radical, and then we get s could be the roots of that characteristic equation are either 0 or minus 1. And so those are in fact the roots of the open loop denominator. So those are actually the open loop poles. So we have one pole at 0 and one pole at minus 1. And so then as we change k, as we increase k, we're going to see this denominator is going to get to the point, and it's going to happen when k is equal to a quarter. When k is equal to a quarter, this radical is now 0. And so anything before that time, anything less than a quarter, this is all just going to be a positive number underneath the radical, which means that we're going to have two real roots. As soon as k hits a quarter, then that means that this radical is 0. And so now we have a double root that happens at minus 1/2. And so that's what's depicted right here. And so the idea that the roots between k is equal to 0 and k is equal to a quarter, the roots are all real, which means that they all stay on the real axis. There's no imaginary component. And so that's why we're drawing these orange lines extending just along the real axis. And then at s equal to minus 1/2, when k is equal to a quarter, that's a double root. So right here, there's a double root. And after that point, as soon as k is greater than a quarter, then the radical is going to be negative, and inside the radical is negative, which makes us have complex valued roots. And so at that point in time, the complex value is just going to essentially keep the same real value, which is the minus 1/2, but it's just going to increase or similarly decrease the value of that those two imaginary poles as we change k higher than a quarter. To see that we can actually use the root locus method on something other than a control loop gain, suppose we have the following system where again we have proportional control and unit feedback, and our control our open loop plant is given by this, which is very similar to what we just worked with, but now we replaced one of our poles with C, and we're going to assume that our controller gain is 1. So in this case, the controller gain is not the variable, but we would like to see what happens to the roots of the denominator of the closed loop transfer function, essentially where do the closed loop poles go as the open loop pole is changed. And so this open loop pole is denoted at minus C. And so we're going to we'd like to figure out what happens as we vary that C, essentially start as this pole, S plus C, we could start that at 0 and then effectively shift it to the left. And so what we're going to see is that we can, even though this is not currently in the right form, we can manipulate this to get it in the right form. So if we were to multiply both sides by S times S plus C, we can get we can simplify that to get this expression. And so then the kind of creative use of the root locus, we can divide both sides by S squared plus 1, and that actually allows us to factor out a 1 and then enable us to get this C, this parameter C that we're interested in varying, as a linear multiplier of a transfer function. And so even though this is not L of S, this is not the loop function, it can play the role as we use the root locus technique. And so the important part is that C now appears linearly in the characteristic equation. And so we have the format of 1 plus this linear parameter that we're going to be varying multiplied by a transfer function and setting that equal to 0. And so this looks just like what we just did. And so now we can apply the same kind of techniques to analyze it. And so here we can use binomial theorem again in order to, or binomial formula again, to write down the roots of this quadratic. And again, we get something that looks like this. And so when C is equal to 0, essentially where you have 2 poles of the open loop plant at 0, then under the radical is negative, and that simplifies to simply just plus or minus I. So the poles start at on the imaginary axis at plus or minus I, and then we notice that at C is equal to 2, that's where this radical becomes 0, and that's going to be a double root. And a double root is always going to be real, and it's going to be real at minus 1. And so we get a double root at this point. And then as soon as C is greater than 2, then we always have real roots. And one of the things we can also observe is that as we let C get really, really large, then the radical term, the 4 doesn't matter so much. This 4 doesn't matter. And so essentially when C is really large, the square root of C squared minus 4 effectively looks like C, which means that if we combine this with the rest of the description of this root, then we'd have minus C over 2 plus C over 2, which would go to 0, which would asymptotically approach 0. And then the other term would be minus C over 2 minus C over 2, which would go off to a minus infinity. And so that's what we're seeing with these green lines, that this goes off to infinity and this one goes to 0. And so before we get into the guidelines of sketching a root locus, it's worth discussing again what the definition of the root locus is. It is essentially the values of S. So it's all the values of S that satisfy this characteristic equation being equal to 0. And so we're trying to identify these values of S because there's no S in 1 or in K. So it's all the values of S that make this true. Another way to interpret that is if we use one of the different ways of writing the characteristic equation, in particular if we let L of S be minus 1 over K, another way to interpret this is the fact that the magnitude of L of S needs to be 1 over K, and the angle, the phase, needs to be pi or some 2 pi multiple of pi. So the phase has to be 180 degrees or some modulo of 360, so it could be 180 plus 360, 180 minus 360, 180 minus twice 360, and so on. And so this is for one of the reasons why this is often called the positive 180 locus. And this distinguishes it from another option that we won't really talk about in this class, which is the negative 0 locus. which means that essentially you're taking in cases where this would be where k is less than 0. So before we get into the last bit of this video lecture, I want to remind you what a difference in Cartesian coordinates. So if we have a complex value s and we have a complex pole p, and we're essentially computing this quantity s minus p, I'd like to remind you what it looks like graphically. And so if our pole is located here, and the point S is located here, both in complex space, then the difference between them is a complex number. And that complex number can be interpreted as having the magnitude of that complex number is actually the distance between these 2 points, the straight line distance, and the phase of that complex number that is the result is the angle that you'd have to point from P to look at, essentially to make P look at S. And so that's always measured from this horizontal. And so similar to some of the other things, for example, when we talked about Bode plots, it became useful to represent our transfer function in terms of polar coordinates. That's what we're going to do to help us understand some of the criteria for drawing the root locus. So we're going to take all of the terms that look like s minus p or s minus z for the zeros, and we're gonna change that into polar form, and that's going to give us criteria on the angles and the magnitudes. And so just to finish that idea up, we're going to relook at this second definition where essentially the magnitude has to be 1 over k and the angle has to be some multiple of 180 modulo 360. And so the value, so we said that the root locus is all the possible values of s that satisfy this condition. And so let's just call that like a test point. Let's test to see, is S0, is that on the root locus? And so for it to be on the root locus, the L evaluated S0 needs to have magnitude of 1 over k and needs to have phase of 180 modulo 360. And so the way that we can kind of interpret that is that, again, we're going to evaluate the numerator and denominator at this test point S0, and then we're going to stick that into all of the terms that are in our transfer function. Once we factor them, all the terms that are the zeros and all the terms that are the poles. And so this is exactly what I was talking about before, where we are going to have this Cartesian difference, and we're going to represent that as a magnitude and a phase. And again, that magnitude is the straight line distance between them in complex space. And the phase is the angle that Z would need to point towards to look at that test point S0. And the same for the poles in the denominator here. And so very similar again to the way that we looked at the Bode plot, we can multiply out all of the magnitudes together and all of the phases together, and we get an expression that looks like this, where we can extract all of the magnitudes, essentially the product of the numerator and the product of the denominator magnitudes divided. That needs to be this magnitude 1 over k. And probably more importantly, what we're going to see more frequently is the fact that when we divide the exponential forms with the sum of phases across these, because when we take the product of each of these terms, we take the product of these terms, and so that leads to the sum in the exponent of all of these angles, psi j in this case. And so this sum, once we take the sum over this and we take the sum over this, and when we divide, this has to equal to -1. And that really just means that another way to rewrite this is this particular term here is that we just have this exponential of e to the I, and then essentially this sum over this psi j minus this sum over phi k. And this minus sign comes from the fact that this originated out of the denominator. And so what this is going to mean is that now this difference, this sum subtracted away from this sum, that that combination needs to be equal to pi, or 180 degrees, again, modulo 360. And so this is one of the key criteria that we'll continue to use when we define our sketching rules.